Okay, so hello and welcome to this video where I will be explaining the project that we did for our course of data science, which is reading digits with deep learning. Most of us often end up wondering sometimes how touchscreen devices recognize the handwritten numbers that we've written that have been written, uh, or maybe how postal services read messy zip codes. This is where the handwritten digit recognition comes into picture. The input that we've used here is the MNIST dataset. This dataset contains 60,000 training images, 10,000 testing images, in which each pixel is 28 by 28, which is around 784 pixels per image. This dataset includes digits from 0 to 9, the images of handwritten digits of 0 to 9. When we basically try to emulate this model, the major problem that we struggled with was that the training was very slow and the accuracy plateaued quite early. So to fix this issue, we normalized the pixel values in a range of 0 to 1 to ensure a faster and more stable training. So this is where we loaded the data and we divided it by 255, which is the max limit of intensity of images lighting up. Moving on to the code, we've imported these libraries, we've trained the data, and this is the array that we were previously dealing with huge variations in the values ranging from 0, 30, 36, 94 to 142, all the way up to 255. Upon normalizing these values, we got this array where all the values are now within the range of 0 to 1. So these are the sample training images. These are the images that were passed with their corresponding labels for the model to be trained upon. So moving on to the training label distribution, this basically shows the frequency of each image appearing in the dataset. As you can see, it is all quite balanced, as if one of them had a much higher frequency than others, the model might overfit to that value. Okay, so now moving forward, we will look at the t-distributed stochastic neighbor embedding. We've imported this TSNE algorithm from the scikit-learn, and we've done this only for 1,000 data because we've done this just for plotting purposes. And this had a shape of 784 pixels because each image in the dataset is 28 by 28. And we've compressed this into just 2 dimensions that has been mentioned here. This plot actually shows how tightly knit or how uh, entangled these values actually are. As we can see, 0, 6, these form quite closely knit structures, clusters. And if we look at this brown, green, and red, which corresponds to 5, 8, and 3 respectively, these are quite entangled in each other. So we can say that the model might make much more errors while recognizing these values as opposed to 0 or 6.
I'm Kriti, and now we'll continue further. So first we have used the one-hot encoding for the labels. Since this is a multi-class problem from digits 0 to 9, we have one-hot encoded the data as it converts each label into a vector. Then we have a model in which we have used the activation function sigmoid. First, we have flattened the data as neural network requires in one dimension. Then we have compiled the data using our optimizer function Adam and using the evaluation matrix accuracy. And then we run it on 100 epochs. So as we can see, and then evaluating on the testing data, we can see that we have achieved the accuracy of 91%. And then we have the model in which we have used the activation function ReLU, which is the hidden layer. We have used this function to avoid the issue which was in the sigmoid function, which was due to the vanishing gradient. And then we have for the output layer, we have used the activation function softmax, which gives us the probabilities of each data. And then again, running it on 100 epochs. Here is the result. And then evaluating the data, we can see we have achieved the accuracy of 97%, which our accuracy has increased drastically. Then again, we are plotting the accuracy for both the models by using the matplot library. We can see the accuracy for the ReLU model is 97%, and that for the sigmoid function is approximately 91 to 92%, which is increased due to the issue of vanishing gradient. Then again, we are using the C1 library and plotting the confusion matrix for our data. As we can see, the x-axis shows the predicted values and y-axis shows the actual values. The actual value was shown to be 9, but a model predicted 0. There were 3 cases.
So hi, this is Himanshi. Now we are going through the misclassified digits. We have shown the misclassified digits, which actually are the digits which our model predicted wrong according to their true values. Here it is the digit which is actually 2, but our model predicted 7. So these are the spaces where our model needs to work more. Now we have shown the classification report. Our classification report shows the precision, the recall, the F1 score, and the accuracy. Here we have taken the model, the ReLU model, which we have taken as the final model or the most appropriate model with accuracy of 98%. Now using the sigmoid history and the ReLU history, we have shown the loss comparison matrix or the loss comparison plot, which actually shows that the sigmoid model took more time to learn than the ReLU model. And actually the accuracy is therefore more of the ReLU model. Now talking about a single data, like we have taken a single data 7 and now check the probability that our model predicts. We can see that the model predicts nearly 1 probability of the model, and hence our model is working great according to it. Now, the kind of digit, this kind of digit recognition system has real-world applications, from automating postal codes leading to digitizing handwritten forms and even in banking check processing. Thank you.